Hello friends, we are still not employed by a FAANG company, so let's not stop lead coding till we get there. Today we are going to do a LeetCode medium problem, longest increasing subsequence, and I have already solved this problem and you can check out the original solution over here. So basically the previously when I solved this problem, I mentioned in that video that I was solving it in big O of n square time, and this would be perfectly good and reasonable to expect from any candidate in an interview. But the thing is, if you want to be an exceptional candidate, if you want to make sure that you don't leave any gaps in your FAANG journey and your so you need to know these things. So that's why I'm creating this video, and in this video we are going to solve this problem in actually big O of n log n time. And the way we are going to do is something called as patience sort. So let's take our custom example, and as I have mentioned previously that it is very important to make custom examples, because using those custom examples you can determine that you have the ability to think and make sure that how can you create your own test cases. So this is our example, and it's quite a long one, but the thing is I need to make sure that I go through all the possible aspects in the given example, and that's why I took so many integers, so it becomes absolutely clear in your mind that how we are going to achieve it. So basically at any given location we can either have a null string, so a subsequence that has no entries, a subsequence that has just one entry, a subsequence that has two entries, so this is null, one entry, two entries, subsequence that has three entries, subsequence that has four entries, and so on. So, and our aim is to find out a longest increasing subsequence that we can achieve. So for this one we are going to use couple of arrays. We are going to put them in a different manner, and as you would have guessed that because the time complexity we get is actually n log n, somehow we are going to use binary sort over here. So uh, let's start the problem. First of all, we are going to create two arrays. First array is to keep track of the longest increasing subsequence that we have found, so whether it's value 1, of value 2, of value 3, whatnot. And second thing is we are going to store the last digit for any given longest increasing subsequence. So what I mean by this last digit is that suppose we find an increasing subsequence over here, that the values 5, 16 and 27 is an increasing subsequence. So in the longest increasing subsequence array we are going to note an entry as 3, where because the length of values are 3, and the last entry we have in this subsequence is 27, and the combination of these two is going to allow us to create some pretty interesting things. So let me go over the example, and I would be explaining every single time what we are doing and how we are finding it, and at the end I'm going to show you that what could be the intuition behind this. So at first location 10, basically we don't have any substring so far. So the current substring we have found up until this point 10 is just a single value 10, and in this single value 10 in our LIS we can create an entry like 1, and the last digit we have for this entry 1 is 10. So we are good so far. Now let's move on to the next one. Now next entry is currently we only have a substring 10. Next entry we have is 7. Now we cannot create an increasing subsequence just by these two pairs, because obviously 10 is greater than 7. But the thing is we can replace this 10 with this 7, and how we can replace it is because up until this point 10 is a substring of length 1 and 7 is also a substring of length 1, so both of us are just same. But the thing is, whenever we move forward all the values that are greater than 10 will also be greater than 7, which means that suppose we have value over here 11, 15, 18, something like this, and if we take it with 10, we would be able to create a longest increasing substring like 10, 11, 15, 18. But the thing is, same thing can be done for 7 as well. So it makes no difference that which entry we keep. But if we have a value that is between 7 and 10, 10 won't be able to do anything in that case. Suppose we have an entry like 8, 9, 11. So in this case, if we would have just considered 10, the longest substring we would be able to make is 10 to 11. That's it. But from 7, we can actually make 7 to 8, 8 to 9, and 9 to 11. This would be of size 4 and this would be only of size 2. So it is in our interest to keep 7 as our longest increasing substring and not 10, because value of 7 is actually less than it. So we will replace this 10 in this array we have created. So currently the last element we have becomes 7, and this 7 is also of just length 1. So we have only kept this one entry and we have basically just discarded it. We have went over it and we didn't find anything good. Now at this point we only have a substring of 7. Now comes the value 8. Now 8 is greater than 7 and 8 is in itself a higher value. So we have two possibilities. Either we can keep 7 as it is as a longest increasing subsequence, or we can have a subsequence like 7 and 8, and we are not appending 8 behind this 7. We are creating that the longest increasing subsequence we have so far of value of size 1 is still 7, but this one is, we are creating a new subsequence that is of size 2, and we are appending this 7 behind 8. So which means we would be creating a new entry over here in our longest increasing subsequence of value 2, and the last element of this value is actually 8. But the thing is, meanwhile the first element is still 7, because we only up until this point, if we consider a substring that is of only value that is to be only of size 1, the best element to choose for size 1 would be 7 because it is the smallest. And this is the main logic behind the patient sort. So let's move on to the next element. Again we go to value 5 now, and the substrings we have so far are 7, 7 and 8, and now we have this 5. So we cannot append this 5 over here, we cannot do anything with this. But the thing is, if we consider these 4 elements and if we consider the substring of size 1, 5 would be the most ideal candidate and not 7, because 5 is actually less than 7. So it is in our interest to replace this entry 7 with the entry 5, and we will update in our array with entry 5. Let's clean this up a bit. Now due to space constraints, we are going to write down our subsequences over here. So far we have found 2 subsequences. One is just 5, that is of size 1, and second one is 7 and 8 that we have stored over here, and we are keeping track of the last digit that we have appended. Again let's consider 16. So now for this 16, and if we consider the last 2 elements, 16 is definitely greater than 5, but there is no point in appending 16 at 5. It is in our best interest to append 16 behind this 8. So our algorithm is basically, what we are doing is we are taking the value from the input, we are checking in our last array to see that what is the best position to fit that value, and the best position to fit that value is to keep the increasing order intact, because notice that previously the value we had was 7 and 8, that was increasing order. Now the value we have is 5 and 8, that is also increasing order. And now the next value 7, next value 16 comes, we can actually append it behind 8. So after 8 we can create a new entry, and we would do that. So we would create a new entry called 3. And why we were able to do a new entry is because this 7 and 8, we are not going to replace 8 by 16. We are actually going to leverage this 7 and 8 because they are already a subsequence, and our aim is to find the longest increasing subsequence. So why would we replace 8 with 16? It's actually in our favor to keep this 7 and 8 and create a new subsequence 7, 8 and 16, so that we can use, because suppose if all the values that come after 16 are like 9, 10, 11, 12, 13, and if we have created a subsequence called 7 and 16, so these all values we would not be able to consider them as our longest increasing subsequence because we don't have this 8. But if we have this 7 and 8 over here, and if these values comes after 16 and we have created a separate entry like this one, 7, 8 and 16, so this is separate in itself, we can actually append all these 9, 10, 11, 12, 13 values behind this 7 and 8, and this would be our longest increasing subsequence. So I hope that this makes things more clear, that why we are choosing to have a new 7, 8 and 16 as substring. And we would create a new entry in our array as well. So now these are the 3 substrings we have. Next value is 27. So 27 is again greater than this 16. So now we are going to create a new entry 7, 8, 16 and 27, and we are going to have a new entry in our LIS with value number 4, and we are going to add the last digit as 27 over here. I hope that what I'm doing is understandable, that why we are actually creating this new entry from the given input. The next value we have is 9. So let's see that where is the best place we can fit this 9. The best place we can fit this 9 is actually after 7 and 8. So like this 9. The thing is, we are not going to replace this 7 and 8 with 9, because up until this point, up until 9, if we see the best pair with 2 entries only, that with the least value is actually 7 and 8. There are multiple pairs that create the that are creating the longest increasing subsequence of length 2, like 5 and 16, 16 and 27, 5 and 27. The thing is, they're all greater values. If we see the last element over here, 7 and 8, the last element is the perfect fit. So that is why we are going to keep the 7 and 8, and we would be creating a new entry at this place. So we are going to replace the 16 with value number 9. So let's update this in our array as well. So for the value 3, the best we can find is 9, and that would be the subsequence 7, 8 and 9. So far we are keeping track of all the subsequences that we have found with the values 1, 2, 3 and 4, and we are also keeping track of the last digit that we have calculated so far. And because all the values are in an increasing order, it becomes very easy for us that whenever we find any new value like this, it becomes pretty easy for us that where we are going to add it in this array and which value we are going to update it. So this is the main logic behind patient sort. Now the next value is value number 1. So where in this array we can store value number 1? It's pretty simple. We can only store it at position 1. No other position we can store. And based on this, we can say that up until this point, if we only have to create a subsequence of length 1, it would be the most ideal to have the last digit as 1, because all the values after that would actually be in an increasing order, and we can replace this 5. In our list of subsequence, we will have entry 1 over here. Now let's consider this value number 13, where over here we can add this value number 13 so that it would give us the most value. And actually we should not be replacing this 9 with value number 13, because we are not trying to achieve a substring like this. Rather than having 7, 8 and 9, we are not trying to get 7, 8 and 13, because that is not in our favor. Because notice that this is already existing and 13 can be appended next to it. So what we can do is, actually we can replace this 4, the subsequence with 4 entries, with this 7, 8, 9 and 13. So our new subsequence would become 7, 8, 9 and the 7, 8, 9 and 13. And why we are able to replace the 7, 8, 9 and 13 with previously 7, 8, 16 and 27? The reason is quite simple, because both generate the value 4, so that is okay. But the thing is, with this 9 and 13, we have higher odds of making longest increasing subsequences for the upcoming values, and which we are going to see right with the next value. So we will update the value 13 over here, and so far these are the 4 subsequences we have. Now the next value is actually 15, and imagine that if we had kept this value as the substring of 4 values, we won't be able to insert 15 over here, because though both of these were same, 15 is easier to be appended over here, but it cannot be appended over here. So that is why in the previous step we actually replaced this value 4 with 13. So I hope this makes it more understandable. Now let's see that what we can do for this value number 15. So the logic is quite simple. We are simply going to append this value number 15 behind this 13. So the new substring, and we are going to keep the value number 7, 8, 9 and 13 as a 4 substring, as a substring of length 4, and we are going to create a new substring 7, 8, 9, 13 and 15, and this would be a new entry in our array. So we will have a substring of length 5, and the last digit for that would actually be 15, and this would be the end of our array. And since we have reached to the end, we just need to iterate over this one and find out that what is the biggest length we were able to find, and we just simply return this value. So this is as simple as it can be. And why we are able to achieve it? Because at every single location, for every single element, we are trying to see that where we can fit that element that best represents that position, and based on it we were keeping track of the longest increasing subsequence. So basically we were intellectually choosing our own longest increasing subsequence, and we are also keeping track of whatever we have calculated in the past. Because if we were to choose a value of 3, that what is the longest increasing subsequence up to the point of 3, we can easily say that hey, it's this one, and the last digit is actually 9. So if we find some better digit, it becomes pretty easy for us to calculate that where we are going to append that value. And I hope this makes things more understandable. Now let's calculate the time and space complexity for this one, and it's pretty simple. That at any given location we are iterating over the entire array, and for any single position we are checking that where we can store that position in this given new array that we are trying to create. But the thing is, this new array is already sorted. So because it is sorted, we can actually achieve that in log n time, and initially we have to iterate over this entire actual input once, so that will take n time. So basically we are calculating this whole approach in big O of n log n time, which is a very good time complexity. Because if you remember correctly, originally for the brute force approach, our time complexity was 2 to the power of n. for the second accepted approach that I completed in last video, our time complexity is actually n square. The thing is n log n, this is a thing of beauty. Now let's move on to coding. And if you still don't understand the concept, I again ask you kindly to go over this example again, because if you can master this, sky's the limit for you. So let's do the coding now. Let's create a new array list. We can start by adding the first element, because the first element would actually be the first list of size 1. And then we will initialize our loop to iterate over the entire input array, and again we will start the loop from second position, I equal to 1. Inside the loop we need to find that whether the given number is it actually greater than whatever the last value we have in the subsequence. If it is, we need to append it to the subsequence. So and we can just add it to the subsequence. If not, we'll need to run the binary search. So, and over here we can just create a new function to run our binary search, and in the input we will provide the substring and current ith value we have. And now let's create method for that. Inside the loop, first of all, we'll create a left and right variable. So left would be of size 0 and right would be of whatever the size we have for the integer for the given input substring. Now we will just run a condition that while left is less than right, we are going to calculate the mid pointer, and then if the mid pointer is already existing, we simply return that value. If not, we either move on the left side or right side. So we'll do left is equal to mid plus 1, else we can simply do right is equal to mid, and after the loop we can return the value of left. Now over here in the J we are receiving whatever the value of left we got, so we add the subset to our existing subsequence. That should be the logic. So after the return we after the end of the loop we just need to return the size of the list, and this should provide the longest increasing subsequence. Let's try to run this code. Looks like we put the values out of order. Yeah, looks like our solution is working. Let's try to submit it. And yeah, see, our solution is actually faster than a lot of other submissions, and that is because our runtime is actually n log n. And I'll be posting this solution in the comments, and hope you like the video. Thank you.